Welcome to Recitation 11, and we'll be going over Boltzmann machines. There'll be two parts to this recitation. So part one will really consist of me reviewing the discussion you went over in lecture and so forth about Boltzmann machines, and the second part of the recitation will be about Jingwei going over the code for regarding Boltzmann machines. So let's get started. So what we will talk about in this part, we'll talk about Boltzmann machines' relationship with Hopfield nets. We'll also talk about how restricted Boltzmann machines known as RBMs. So what is a Boltzmann machine doing? They're quite similar to a Hopfield network in that the visible nodes are but the visible nodes are not deterministic. They're actually stochastic, and there's a state of the Boltzmann machine, whether if it's under 0 it'll be off, and when it's over 0 it'll be on. And then for activation of these nodes, it'll be determined by a Bayesian distribution. Okay. So the Boltzmann machine was actually created by Dr. Hinton in 1985, and it was a generative supervised model involved learning probability distributions from data sets. And in this one, you'll see two Boltzmann machine formulas. So where each node has two states of it being 0 or 1, and one has the ability to update its state. So in this function, we take in basically a bias, Sj, which is the current state of the unit, and Wij, which is the connection strength between j and I. And this gives us the energy function for a given state. And then we pass this on to our activation, which is a logistic function, which ranges between 0 and 1, and we can interpret it as a probability distribution to turn on a given state. And our network will eventually reach some Boltzmann distribution or some equilibrium over time. So this equilibrium state, pretty much. The network runs by repeatedly choosing a unit, resetting its state. After running for long enough, at a certain temperature, the probability of a global state of a network depends only on its global state's energy, and not on the initial state it started at. This means like the log probabilities of a global state become linear in their energy. The relationship is true when the machine is at a thermal equilibrium, meaning that the probability distribution of global states have converged. So usually you run the network at a high temperature, and it gradually decreases to a lower temperature and reaches some thermal equilibrium. It usually fluctuates around this global minima, changing slightly, and this process is called stimulated annealing. Here we have the energy state, pretty much, of our whole function, and the differences in the global energy, the results from it, is given by this function over here on to the right. And this can be expressed as the different energy of two different states, and our goal is to basically minimize it. You will also have two distributions. One is the distribution of the data itself, and the other is the distribution of the hidden units itself too, and that'll be more talked about when we're discussing training. So training these networks. So usually the units in the Boltzmann machines are divided into visible units and hidden units. The visible units receive information from the environment, which is usually the training set, which is a set of binary vectors, and it's detonated maybe some p of v. And the other one is some p of positive v, and the other one is maybe we denote or as p of negative v for the hidden units, as such forth. So our goal is to approximate this real distribution using the hidden units produced by the machine. And we measure the similarity of these two distributions by the KL divergence. And our goal is we can update the weights using this KL divergence. So we take the log p of v, pretty much, which is a function of weights since they determine the energy of the state, and the energy denotes the p negative of v, as promised by our Boltzmann distribution, and we run gradient descent over this log p of v by subtracting the partial derivative of g with respect to the weight. And the training involves two different phases, which is the positive states, which are what the visible unit states are clamped to their particular binary state vector. Others are negative, which is they're allowed to run freely, which is our negative values, which are our hidden nodes. And our goal is to basically minimize our energy function, which we discussed earlier, and to determine what these weights would be. Okay. However, there's some particular issues with Boltzmann machines that are not usually that are not that's the reason we use RBMs. So usually is that the Boltzmann machine is rather a general computational median, and we usually train it on maybe something, for example, say photographs. The machine would theoretically learn this distribution of photographs, and then we can maybe complete a partial photograph that was given to us. However, there's a practical problem to this. So when you reaches these larger sizes of these networks, the machine itself doesn't learn too much, and this is due to two important issues. The required time to order to collect equilibrium grows exponentially with the machine size and with the magnitude of the connection strengths. Also, the connection strengths are more plastic when the connecting units have activation probabilities intermediate between 0 and 1, leading to some variance trap, and this causes some noise in the whole thing. So this allows us to really reach to restricted Boltzmann machines, as they could be quite efficient quite efficient. So in this diagram below, you have a graphical representation. So here you have 4 visible units and you have 3 hidden units. So in restricted Boltzmann machines, there are only connections between hidden and visible units, not between units of the same type. And there's no hidden connections, nor are there the visible connections. And in this restricted Boltzmann machine, we actually get we get a different energy function that's of matrix form. And basically, you'll have this matrix form energy function, pretty much. And it was initially, the energy function is actually very analogous to the Hopfield network, as in general Boltzmann machines, the probability distributions over hidden and over visible networks are defined in terms of this energy function as well, where z is some partition function discussed over here. And this partition function basically is over all possible configurations to ensure the probability distribution sums to 1. And below you'll see the individual activation probabilities are given by the following formula, where it's based on a logistical sigmoid function as well. Over here. Sorry, discussing these two. They represent, so RBMs are very powerful and they represent complicated distributions compared to really Boltzmann machines. And now we'll move on to deep Boltzmann machines. So which is basically has multiple hidden random variables in the network. Versus where our RBMs did not have that. So in this area, you'll see you have multiple hidden layers, versus where you just have a particular visible layer, a hidden layer, and then an act followed by an activation function. And so the activation functions will actually follow to another hidden layer, and so forth. Deep Boltzmann machines can learn complex and abstract internal representations of different tasks, such as speech recognition and so forth. And that's the whole reason we use deep Boltzmann machines. And that now I'll be discussing really about the reconstruction of them and like the forward pass and comparing them. So when we do backwards, the feed activations into the reverse manner pretty much. These are basically the new input. The activations are the new input. Also, the biases in the reconstruction are new. So these are actually brand new parameters in the model. And the hidden biases basically in the forward, these are the hidden biases over here are basically different. They produce activation in a forward pass, but in an RBM reconstruction, but it helps for RBM reconstruction on a backwards pass. From a probability perspective, you make predictions of activations based on weights and inputs. In reconstruction, we want to estimate X based on activations, and we want to combine them to get joint distributions. So in the forward pass, we have the probability of activations given by X and W. But in the reconstruction, we have the probability we want to get the inputs. So we have the probability the inputs is given by the activations and the weights itself. And we could kind of form this joint distributions. And let's assume maybe we get something that both the distributions follow some normal curves too. So our goal over here is we have P of X which is our forward pass, and Q of X which is our backwards pass. And then our goal is to kind of minimize the differences between them, which we discussed earlier when we were training a basic Boltzmann machine. So you basically use a KL divergence in order to minimize minimize these areas, and that's the goal of basically deep Boltzmann machines. This is kind of just a small review regarding all of these topics, and I think now Jingwei will take over regarding the code and so forth.
Now let's take a look at the implementation of these Hopfield networks. At the very beginning, there are some helper functions that will be very useful. The rescale function takes torch tensor of vectors that only consists of 0 and 1s. So it uses 2 times x minus 1 to convert 0 to minus 1 and 1 to stay the same. It is used together with the discretize so that it takes the values and all the negative values will be minus 1 and all the positive numbers will be 1. So it just make all the values to be either minus 1 or 1 with the help of the rescale. And the gamble noise logits function takes a template and it returns random numbers that have the same shape as the template. It is used here in the noisy fields that takes fields and temperature. It generates two noise, one's add noise and sub noise using the gamble noise logit function, and it subtracts these two noise together and times the temperature and apply it to the fields. Basically, the temperature controls how much the noise can affect the fields. If we have a higher temperature, then there are a greater chance that the fields will be affected. Okay, so that's noisy fields. And the update function is just an in-place function to align the sign of the values to their corresponding fields. As we learned in the lecture, each neuron flips itself to match the sign of the corresponding field. So that's exactly what the update does. And it is implemented in place. The abstract loop net is an abstract class that all other networks inherit from. It takes an input called the number of units, and which defines how many neurons the network has. In the init weights, there is a parameter called fixed weights. If it's true, then it will call the fixed weights. What the fixed weights does is basically forces the weights to be symmetrical, so that updating node J from node I will be the same as updating node I from node J. And it is accomplished by some matrix multiplication and makes the average of the weights. Yeah. And the compute fields is not implemented because every network may have their own implementation, and it defines how they compute fields uniquely. And the compute energy is very simple. It just takes the values and compute the fields according to the formula and returns the energy based on the definition. So that's very simple. And our update function is not implemented as well because different networks may have different way to update. And the run iteration, namely it runs the model for a few iterations and return the values. For each iteration, it computes a field and updates the values, and then it returns the values. The for function just calls the run iteration function, and the inference function is used in the stochastic network. So the reason is that, what it does is basically it runs the iteration for a few times according to the input, and then it create a empty box have the same shape as the values, and then it runs the number of inference iterations. What it does is it computes the fields and update the values, and it adds the values to this container, and then this container will divide by the number of inference iterations, so it will become average, and we return the discretized value of the averaged values. And the reason why we did that is because stochastic networks, the final result after a few iterations may not be the best. So we want to run it a few iterations, and then we want to get averaged value to be more representative, rather than just return the final output. So that's basically the inference. Okay, so now let's take a look at the Hopfield network. The weights is defined by a tensor of number of units by a number of units. That's very trivial since every neurons in the network can connect with other neurons. So we will have the shape, the weight will have the shape look like this. And the compute field is just multiply the weights by the values. And that returns a field. And the unsqueeze and this is just to make the shape identical to each other so that we can apply the mathmul function. And the update function, we just use the update function on the values and fields. So it is very simple if we know about the update. As we discussed earlier, the update function is just to make the values to have the same sign of their corresponding fields. So, namely, if its corresponding field is positive, then it will be 1, otherwise it will be -1. Okay, so that's the update function. And the stochastic Hopfield network is basically the same as the Hopfield network. They have the same init function. Since it's stochastic, so it has a temperature. And the compute fields is the same. And the update function is basically the same, but it returns it passing the noisy field instead of the fields. So the noisy fields, as we talked about earlier, is just add some randomization to the fields. So how likely this randomization will affect the fields is determined by the temperature. So that's the stochastic Hopfield network. And okay, now let's look at the Boltzmann machine. The Boltzmann machine introduces the hidden layers, the hidden neurons. So the hidden units serves to increase the capacity, but whose actual values are not important. So these hidden values does not store any pattern, but just help the visible neurons to store the pattern. And as you can see, the Boltzmann machine is also stochastic, so it has a temperature as the parameter. And we also, taking the, okay, that's fine. Okay, so the compute fields function is identical, so we can just ignore that. The update function, there is an extra parameter called include visible. Sometimes we do not want to update the visible units, but only update the invisible units. Namely, we do not want to update the visible unit in the expand data. We will talk about it later. But how do we do that? That's just we just preserve the old values of the visible units, and then if we do not want to include the visible units, we just restore the value from the old values. And this is identical to the stochastic Hopfield network. We called update function on the values and give it noisy fields. So that's update function. Okay, so I'm going to explain the expand data. What this function does is basically generating hidden units from the visible units. So we are going to take the visible values. So this in does not mean invisible. This is visible units. The in just means input, and so that's something we need to notice. And we have the batch size visible values and hidden values and the value list. So this is what we're going to return. So we will first start with random. So we will first randomly initialize the hidden values and then let the network iterate for a few times and see what the hidden values end up being. And we will append these hidden values and return it together with the visible units. Okay, so that is expand data. As we talked earlier, it basically takes the visible values and generates hidden values. And then we have the restricted Boltzmann machine. Namely, it's more restricted than the regular Boltzmann machine in a way that the hidden units cannot talk to each other, and the visible units cannot talk to each other. The only connection allowed are between the hidden units and the visible units. So the compute fields are a little bit different because since the hidden layers cannot talk to each other and visible units can talk to each other, so they have to be computed independently, and then we concat them together. So that's compute fields. And the update function is quite the same. We call the update function with the values and the noisy fields. And the expand data is a little bit different than the regular Boltzmann machine because of the restrictions. So now, since we are going to preserve the visible values, so the visible values does not change, and the hidden values are only determined by the visible values, so we can just calculate them deterministically instead of going through some loops. So that's what we got. Okay, so till now we have gone through all the models, and the rest of the code just training wrappers that helps the training. We are not going to discuss any detail. Get the Jupyter notebook of this recitation and see how our models can apply to the real dataset. So before that, we may want to install some packages to satisfy the dependencies, and then we import a few things, and we load the MNIST dataset using a helper function. And the MNIST dataset is consists of 84 by 84 images, and we also append a one hot vector after the image. So the 28 by 28 is 784 pixels, and we append a one hot vector. In total, it becomes 794 dimension. So that's our data. And for the Hopfield network, we load the network trainer, and we train it for 300 epochs with the batch size 500 and the learning rate. This equals to 0.001, and with the identity loss. So after we train the model, we so first we modify the first example by setting the one hot vector out to -1, so that the label now becomes 0, and then we apply this. We take this example and put it in the network and run it for 1,000 iterations, and we got the example EV. So if we plot the example EV, we can see the image is very same to the original ones, but the one hot vector is restored. So it's so that means the network actually learns 1 and it restores it to 1. And for the stochastic Hopfield network, we did the same, and we removed the one hot vector for this 6. And as you can see, after we apply the network and run it for 1,000 epochs, it becomes something like 4. That means it's not learning very well. It may not learn 6 very well, so it's predicted to 4. and generate something ugly. Yeah, and this is the restricted Boltzmann machine. We load the network, initialize it with the hidden unions to be 500, and the temperature equals to 0.2, sorry. And we train it for 200 epochs with 500 batch sizes, and the learning rate equals 0.001. And we do the same to the first image, and we want to predict, yeah, and we run the network for 550 epochs, 50 iterations, and then plot the graph. As you can see, the 3 is restored, and it looks like 3 as well. And if we use inference, as we talked earlier, inference is a way that we can reduce the randomization by averaging. So after averaging, then as you can see, it looks cleaner than the network forward, and it restores the label as well. So that's great. And if we take another example here, we remove the label, and then we apply the dropout to make it noisy. So this is the original one after removing the label, and this is what we apply the dropout. As you can see, the one-hot vector is also changed, and this is if we apply the inference to this noisy image, and we get something like this. This is pretty close to the original image, and the one-hot vector is restored successfully. So that's basically our Jupyter Notebook part of the recitation, and you can run it for your own interest as well. Yeah, thank you.